Have you ever wondered why the universe is so perfect for the existence of life? Is it all a coincidence, or is there a higher intelligence behind the creation of the cosmos? Human curiosity about the universe has been constant since ancient times. From the Greeks, with philosophers like Anaximander and Aristarchus, to modern astrophysicists, the quest for answers about the composition, origin, and destiny of the universe has been one of the greatest drivers of scientific advancement. The desire to understand our place in the cosmos and the nature of reality has fueled discoveries and theories that have shaped our view of the universe. This quest for knowledge is a fundamental characteristic of humanity, guiding us in our exploration of the cosmos. The ancient Greeks made the first attempts to understand the universe, believing that air was the primary substance that held everything together. They saw the cosmos as an orderly whole and sought rational explanations for natural phenomena. This rational and investigative approach laid the foundation for the development of science and astronomy, allowing future generations to build on these early insights and expand our understanding of the universe. Today, with the help of advanced telescopes and cutting-edge technologies, we continue to explore the mysteries of the cosmos. Telescopes like the Hubble and the James Webb provide us with unprecedented views of the universe, revealing incredible details about the formation of stars, galaxies, and other cosmic phenomena. These discoveries not only satisfy our curiosity but also raise new questions, pushing science to new heights of understanding and discovery. The history of theories about the cosmos is long and fascinating, full of paradigm shifts that have shaped our understanding of the universe. Greek philosophers were among the first to systematically try to understand the cosmos. Anaximander, for example, proposed that the universe was infinite and eternal, while Aristarchus suggested that the Earth orbited the Sun, a revolutionary idea for its time. These early attempts to describe the universe demonstrate a deep curiosity and desire to understand the world around us. Moving forward to the Middle Ages, Ptolemy's geocentric theory dominated astronomical thought for over 1,000 years. Ptolemy proposed that the Earth was at the center of the universe and that all planets, including the Sun, orbited around it. This model was widely accepted until it was challenged by Nicholas Copernicus in the 16th century. Copernicus revolutionized astronomy by arguing that the Sun was at the center of the universe, introducing the heliocentric theory. This shift in perspective marked the beginning of a new era in science. With the advancement of science, figures like Johannes Kepler and Galileo Galilei refined Copernicus's ideas, facing significant resistance from the Catholic Church. Kepler discovered that planets move in elliptical orbits, while Galileo, with his telescopic observations, provided empirical evidence for the heliocentric theory. In the 17th century, Isaac Newton developed the laws of motion and gravitation, unifying the heavens and the earth under the same physical laws and revolutionizing our understanding of the cosmos. These advancements paved the way for modern physics and the scientific exploration of the universe. For over 1,000 years, Ptolemy's geocentric theory dominated our understanding of the cosmos. Proposed in the 2nd century, this theory placed the Earth at the center of the universe, with the Sun, Moon, and planets orbiting it in complex circular paths. Ptolemy developed a detailed mathematical model that explained the apparent motions of celestial bodies, including planetary retrogrades, which were seen as evidence of an orderly, Earth-centered cosmos. The geocentric theory not only shaped astronomy but also influenced the philosophy and theology of the time. The idea of an Earth-centered universe aligned with many religious beliefs, especially in Christianity, where the Earth was seen as God's special creation. This model was widely accepted for centuries and became an integral part of teaching and culture. Any questioning of this view was seen as heretical until the 16th century when Nicholas Copernicus presented a radical alternative. Nicholas Copernicus, a Polish astronomer, proposed the heliocentric theory, placing the Sun at the center of the universe, with the Earth and other planets orbiting around it. His work, De Revolutionibus Orbium Coelestium, directly challenged the geocentric view, suggesting that celestial movements could be explained more simply and accurately with a heliocentric model. This revolutionary idea laid the foundation for a new era in astronomy and initiated a profound shift in how we understand the universe and our place in it. In the 17th century, Johannes Kepler and Galileo Galilei were central figures in the scientific revolution that followed Copernicus's heliocentric theory. Kepler, with his laws of planetary motion, demonstrated that planets orbit the Sun in ellipses, not perfect circles, correcting a crucial error in ancient astronomy. His discoveries were based on meticulous observations and precise mathematical calculations, providing a solid foundation for modern astronomy. Galileo, in turn, used the newly invented telescope to make revolutionary observations that challenged established ideas about the cosmos. He observed Jupiter's moons, Venus's phases, and sunspots, evidence that supported the heliocentric theory and showed that not all celestial bodies orbited the Earth. Galileo faced strong resistance from the Catholic Church, which saw his discoveries as a threat to the geocentric view of the universe, resulting in his famous trial for heresy. In the following century, Isaac Newton further revolutionized our understanding of the universe with his laws of motion and the law of universal gravitation. Newton showed that the same physical principles governing movements on Earth also apply to celestial bodies. His work, Principia Mathematica, unified terrestrial and celestial physics under a set of mathematical laws, showing that gravity is a universal force acting between all objects with mass. Newton's contributions laid the foundation for classical physics and paved the way for the modern era of science. In the early 20th century, Albert Einstein revolutionized physics with his general theory of relativity. Published in 1915, this theory changed our understanding of gravity, suggesting it is not a force between masses, as Newton proposed, but a curvature of spacetime caused by the presence of mass and energy. According to Einstein, massive objects like stars and planets deform the fabric of spacetime, and this curvature influences the movement of other objects, including light. Einstein developed general relativity from his special theory of relativity, which introduced concepts such as time dilation and space contraction at high speeds. General relativity, however, took a step further by integrating gravity into the structure of spacetime. This theory predicted phenomena such as the precession of Mercury's perihelion, the deflection of starlight by the Sun, and the existence of black holes. The confirmation of these predictions in subsequent observations solidified general relativity as one of the most successful theories in modern physics. General relativity had profound implications for cosmology, opening new possibilities for understanding the universe's origin and destiny. It predicted the universe's expansion, something Edwin Hubble confirmed by observing that distant galaxies are moving away from us. This led to the acceptance of the Big Bang theory as the dominant cosmological model, suggesting that the universe had an explosive beginning from an extremely dense and hot state. General relativity also predicted the existence of gravitational waves, first detected in 2015, providing a new tool to explore the cosmos. The discovery that the universe is expanding was one of the greatest revolutions in modern cosmology. In the late 1920s, Edwin Hubble, using the Mount Wilson Observatory's telescope, observed that galaxies are moving away from us in all directions. He discovered that the speed at which a galaxy recedes is proportional to its distance from Earth, a relationship now known as Hubble's law. This observation provided the first evidence that the universe is not static but dynamic and expanding. Hubble's discovery had profound implications for understanding the universe. It suggested that if the universe is expanding now, it must have been smaller in the past. This led to the idea that the universe had a beginning, an initial point of expansion that scientists call the Big Bang. The Big Bang theory proposes that the universe began from an extremely hot and dense state about 13.8 billion years ago and has been expanding ever since. The universe's expansion also led Albert Einstein to reconsider his general theory of relativity. Initially, Einstein introduced a cosmological constant into his equations to allow for a static universe, as he believed the universe could not be dynamic. However, after Hubble's discovery, Einstein recognized that this constant was unnecessary and called it his greatest blunder. The acceptance of the universe's expansion further solidified general relativity as the foundation of modern cosmology, helping scientists better understand the cosmos's evolution. The Big Bang theory is one of the fundamental pillars of modern cosmology, offering an explanation for the universe's origin and evolution. Initially proposed by Georges Lemaître in the 1920s and later developed by other scientists, this theory suggests that the universe began from an extremely hot and dense state about 13.8 billion years ago. Since then, the universe has been expanding and cooling, allowing the formation of particles, atoms, stars, galaxies, and eventually, life. One of the strongest pieces of evidence for the Big Bang theory is the cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson. This radiation is a remnant of the Big Bang's heat, now cooled to just 2.725 Kelvin, permeating the entire universe. The uniformity of this radiation in all directions suggests that the universe was homogeneous and isotropic in its early stages, supporting the idea of an explosive and expansive beginning. The Big Bang theory is also supported by the observation of the abundance of light elements like hydrogen and helium, formed during the universe's first few minutes in a process known as primordial nucleosynthesis. The proportions of these elements in the current universe match precisely the predictions made by the Big Bang theory. Together, these pieces of evidence provide a coherent and robust picture of how the universe began and evolved over time. The theory of cosmic inflation was proposed in the 1980s by Alan Guth to address some fundamental problems with the standard Big Bang model. According to this theory, the universe underwent an extremely rapid exponential expansion during the first moments after the Big Bang, about 10 to the minus 36 to 10 to the minus 32 seconds. During this inflationary phase, the universe grew unimaginably large, stretching tiny quantum fluctuations to cosmological scales. Cosmic inflation explains several characteristics of the observable universe. First, it resolves the horizon problem, which questions how regions of the universe that are so far apart can have the same temperature and density. Inflation suggests that these regions were very close in the past before being rapidly separated by the inflationary expansion. Second, it addresses the flatness problem, explaining why the universe appears to be geometrically flat. Observational evidence supports the theory of cosmic inflation. In 2014, the BICEP-2 experiment announced the detection of B-modes in the polarization of the cosmic microwave background radiation, initially interpreted as proof of primordial gravitational waves generated during inflation. Although this discovery was later contested due to interference from cosmic dust, the search for signs of inflation continues, and many cosmologists consider inflation an essential component for understanding the universe's early evolution. The observable universe is vast beyond our imagination, containing approximately 2 trillion galaxies, each with billions or even trillions of stars. When we look at the night sky, we see only an infinitesimal fraction of the cosmos. The universe's scale challenges our understanding and makes us question our insignificance and place in such a grand scene. From star clusters to superclusters of galaxies, cosmic structure is as diverse as it is immense. Each of these galaxies is a dynamic system, housing not only stars but also planets, moons, asteroids, and comets. Within these galaxies, stars form stellar systems, many of which have planets orbiting them, potentially capable of harboring life. The distances between these objects are equally astounding. For example, the nearest galaxy to ours, Andromeda, is about 2.5 million light-years away. This vastness gives us perspective on how small and precious our planet is in the cosmic context. The idea of a multiverse further expands these limits. The multiverse theory suggests that our universe may be just one among many, each with its own physical laws and constants. This hypothesis, which arises from some interpretations of quantum mechanics and string theory, proposes the existence of multiple universes coexisting in parallel dimensions or different regions of spacetime. If true, the reality we know may be just a small part of a much larger and more complex reality. The discovery of dark matter and dark energy has transformed our understanding of the universe. Dark matter, which makes up about 27% of the universe's mass, is a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. It is essential for explaining the rotation of galaxies and the formation of large-scale structures in the cosmos. Without dark matter, galaxies would not have enough mass to stay together. Dark energy, on the other hand, accounts for about 68% of the universe's total energy and is responsible for the cosmos's accelerated expansion. Discovered in the 1990s through observations of distant supernovae, dark energy is a mysterious form of energy that acts against gravity, causing the universe to expand at an increasing rate. The nature of dark energy is one of modern cosmology's greatest enigmas, and its discovery led to a significant reformulation of cosmological theories. Together, dark matter and dark energy make up about 95% of the universe's total content, leaving only 5% for the matter and energy we know and understand. This impressive imbalance shows how much we still have to learn about the cosmos's composition and functioning. The quest to understand dark matter and dark energy continues to be one of the most exciting frontiers in science, with ongoing experiments and observations worldwide. The physical constants of the universe are precisely adjusted in a way that allows the existence of life as we know it. From the strength of gravity to the electron's charge, these fundamental values are incredibly specific and interdependent. Small variations in any of these constants could result in a universe unable to sustain stars, planets, or life. This precision raises intriguing questions about why the universe is exactly as it is, suggesting the possibility of intentional design or the existence of multiple universes with different constants. For example, the gravitational constant determines gravity's strength, and if it were slightly stronger or weaker, stars might not form or burn their fuel too quickly to support life. Similarly, the strong nuclear force, which holds protons and neutrons together in atomic nuclei, is precisely tuned. If it were a bit weaker, the only elements in the universe would be hydrogen and helium, making the formation of heavier elements necessary for life impossible. Another crucial constant is the cosmological constant, associated with dark energy and the universe's accelerated expansion. If this constant were different, the universe might have expanded too quickly for galaxies to form or collapsed on itself shortly after the Big Bang. The existence of these finely tuned constants raises the question, were they deliberately set to allow life, or are we living in one of many universes where the conditions happen to be right? The anthropic principle is an idea suggesting that the universe must be suitable for the existence of conscious observers like us. In other words, the conditions we see in the universe are not mere coincidences but necessary for our existence. This principle comes in two forms: the weak anthropic principle, which states that the universe must have properties that allow life because we are here to observe it, and the strong anthropic principle, which suggests that the universe is somehow compelled to generate life. The anthropic principle is often used to explain the fine-tuning of physical constants. The strength of gravity, the cosmological constant, and other fundamental constants seem precisely tuned to allow for a habitable universe. If any of these constants were slightly different, stars wouldn't form, galaxies wouldn't exist, and life as we know it wouldn't be possible. The anthropic principle suggests that we observe these conditions because, in a universe where the conditions didn't allow for life, there would be no one to make these observations. Despite its appeal, the anthropic principle is not a scientific explanation but a way to interpret observations. It generates debates among physicists and philosophers about the meaning of these cosmic coincidences. Some argue that the anthropic principle is a tautology and does not offer a true explanation, while others see it as an important clue to understanding the universe's nature. Either way, it remains a fascinating discussion point in modern cosmology, leading to new questions about the cosmos's purpose and origin. Modern cosmology faces considerable challenges in the quest for a unified understanding of the universe. One of the scientists' greatest ambitions is to find a theory of everything, unifying all of nature's fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Currently, Einstein's general theory of relativity explains gravity on large scales, while quantum mechanics describes the other three forces on subatomic scales. However, these two theories are incompatible in many aspects, especially in extreme conditions like those found in black holes or the Big Bang. One of the most promising candidates for a theory of everything is string theory, which proposes that fundamental particles are not points but tiny vibrating strings. The way these strings vibrate determines the particle's properties. String theory unifies gravity and the other forces, but it still lacks direct experimental evidence to confirm it. Moreover, string theory suggests the existence of extra dimensions beyond the 3 spatial and 1 temporal dimension we experience, further complicating our understanding of the universe. Besides the quest for a theory of everything, cosmologists are also investigating the nature of dark matter and dark energy, which make up most of the universe but remain mysterious. Experiments are underway to detect dark matter particles and better understand dark energy. These investigations may not only clarify the universe's composition but also provide new clues about its origin and final destiny. Modern cosmology is, therefore, a vibrant and evolving field, driven by new discoveries and theories that continue to expand the limits of our knowledge. Throughout this video, we have explored some of the most profound and mysterious questions about the universe's origin and nature. The scientific discoveries and theories we discussed suggest that the universe is an incredibly complex and finely tuned place, raising the possibility of intentional design. Whether you are skeptical or not, it is undeniable that these questions invite us to reflect on our place in the cosmos and the nature of existence itself. If you enjoyed this content and want to continue exploring these fascinating mysteries, subscribe to our channel and turn on notifications. This way, you won't miss any of our videos about the universe's curiosities. Thank you for watching, and see you next time.